Today we know the history of our home planet. The development of science has given us this opportunity. We know that the Earth is about 4 billion years old. At first it was very hot, and after some time as it cooled down, life appeared on it. Paleontologists and geologists have divided the history of our planet into geological eras, each of which had its own types of living creatures, including our favorite dinosaurs. But is everything really so smooth in the official tables and datings? What is modern archaeology, paleontology, and geology based on? Who, when, and most importantly, why were all these dates introduced? We will try to find answers to these and other questions together. As usual, we'll start with the official position, and then we'll delve into the issue from an unexpected point of view. You're watching the channel Age of Distrust with Mikhail Kalmykov. Make yourself comfortable. The story will be long and, I hope, interesting. The entire history of the Earth can be conventionally divided into two huge parts, the so-called eons. One of them is the Phanerozoic eon, which is the one we are living in right now. The name consists of two words from ancient Greek phaneros, meaning visible, and zoe, meaning life. That is, visible life. Almost all living creatures, almost all of life's evolution, from the first single-celled organisms up to humans, is contained within it. And this eon begins about 550 million years ago with the Paleozoic era, more precisely with the Cambrian period. Its beginning was marked by the so-called Cambrian explosion. No, it's not what you think. This was an explosion in the best sense of the word, when there was an explosive growth of biological species. Just before that, Earth was quite a dull planet, with only the most primitive single-celled organisms. And suddenly, as if by magic, like Jack in the Boxes, more and more complex species of living creatures began to appear one after another. The second eon in Earth's history is the Precambrian period. It lasted for almost 4 billion years and existed before the Phanerozoic. By the way, at first it was called the Cryptozoic, which translates roughly as hidden or secret life. That is, it was unknown whether any life existed at that time. However, remains of worms, algae, and bacteria were still found, and that's why this period is now more often called the Precambrian. What exactly happened back then is still unknown. There is a theory about the redistribution of masses on the planet. When the split megacontinent Pannotia caused an imbalance in the Earth's rotation, the continents began to move rapidly toward the equator to take their proper places. But that's just one theory. It's up to you to believe it or not. And the conversation right now isn't exactly about that. It was what it was. In the Cambrian period, there was an explosive growth in the number and quality of biological species. From then on, life only continued to develop more and more. One period replaced another. Some species devoured others, and notably, many of these periods, more precisely 5 out of 8, ended with global extinctions. One of the most well-known extinctions is the Cretaceous-Paleogene extinction, which happened 65 million years ago as a result of a meteorite impact. As a result, all the dinosaurs died out. Almost all animals went extinct. However, birds survived. By the way, to be fair, I should say that there are actually many theories about what caused this extinction. However, 4 main theories link it in one way or another to a cosmic disaster. The only difference is in the details. In one version, a meteorite fell. In another, a comet. In the third, many meteorites at once. And in the fourth, there was even a supernova explosion. So in any case, the causes came from space. And at that time, more than 30% of all living species on Earth went extinct. Another extinction, which is less well known but no less, and perhaps even more, sudden, is the Triassic-Jurassic extinction. It happened almost 200 million years ago and also wiped out about 30% of all living species. its causes are even more unclear. That is, again, the most likely cause is an asteroid impact. But since no actual crater was found, scientists let their imagination run wild and various theories emerged. With volcanic eruptions, again sudden ones, also sudden warming, as well as fluctuations of the world ocean. Although how changes in sea level could have caused the extinction of marine creatures, no one explains. The Devonian extinction happened about 300 to 75 million years ago and was a bit weaker. About 20 to 25% of living species went extinct. The causes of this extinction are also not exactly known, but among the possible theories is, once again, a meteorite impact. Although there are other possibilities, such as the explosive evolution of plants, and once again, changes in climate and atmospheric composition. In the Ordovician period, one of the most serious extinctions occurred. This was about 450 million years ago. At that time, almost 85% of marine species became extinct. And again, among the causes of extinction, cosmic factors prevail, namely the Earth passing through a trail of cosmic dust as a result of the destruction in space of a huge asteroid more than 150 kilometers in diameter. This led to a cooling of the planet and everything else that followed. But the most severe extinction in our entire history is the Permian Extinction, which occurred 250 million years ago. At that time, more than 96% of all marine species and 73% of terrestrial vertebrates died out. This is the only extinction that became mass even for insects. In total, more than 55% of all species, in fact, all living creatures on Earth, died out. And again, the culprit was an asteroid impact. Direct evidence of such an impact has not been found so far. However, numerous indirect clues found in Australia and Antarctica, such as shock metamorphosed quartz grains, inclusions of extraterrestrial gas, and others clearly point to an impact. As we can see, the history of life on Earth fits into 550 million years, during which massive asteroids have collided with the Earth at regular intervals. For the remaining 4 billion years, life on Earth was extremely primitive, consisting mainly of single-celled organisms and various worms. This is roughly what the overall picture of the history of evolution on Earth looks like through the eyes of official scientists. What are their conclusions and datings based on? Radiocarbon analysis. So, how exactly does the radiocarbon method work? The thing is, living organisms contain quite a lot of carbon, including its radioactive isotope, carbon-14 naturally. This isotope continuously emits radiation and decays, and the process of decay, in turn, is a mathematically precise mechanism. Thus, by measuring the residual activity of carbon, you can determine the time of the organism's death. It sounds great, if not for two nuances. The first nuance is the actual decay time of such carbon. It is known that the complete half-life of carbon-14 is 5,730 years, give or take. That means dating objects older than 5,730 years with its help is simply impossible. How could there be millions of years? Of course, there are some calibration curves that take additional factors into account, but even with these adjustments, the maximum dating age is 55,000 years, so there can be no talk of millions of years at all. And the second nuance is about how carbon-14 is actually formed. If you think that it is produced by the living organism itself, you are mistaken. This isotope is formed in the Earth's atmosphere at an altitude of about 12 kilometers due to the impact of solar radiation. Then it immediately combines with oxygen and forms carbon dioxide. Only after that do plants and algae absorb this gas through photosynthesis. And possibly this plant will be eaten by a herbivore, or maybe a fish, and then perhaps this herbivore will be eaten by a predator. or maybe not. Then microorganisms will eat it, and when they die, their remains will once again end up, this time through the soil, in plants, which will again be eaten by a herbivore. And the cycle can repeat forever until the isotope completely decays. In other words, the carbon atom itself could have formed in the atmosphere a long time ago, and only after 5,000 years enter an organism, where it will immediately decay. Or it could enter an organism right away, and then into another organism that eats it, then into a third, a fourth, a 10th, and so on. It will travel through organisms for all 5,700 years. Of course, you might argue that there is certainly more than one molecule of such carbon left in the remains of an organism. And the calculation is probably done based on some average value, maybe. But considering that only a little over 7 kilograms of this substance is produced in the Earth's atmosphere each year, and its total amount is only about 75 tons for the entire Earth's biosphere, you can imagine that there is very little of these isotopes in an organism. And the very appearance and further evolution of carbon-14 is a story that deserves a separate discussion. However, our story is about dating methods, not that. Thus, we have the radiocarbon dating method at our disposal, which has a dating limit of only 5,700 years, and the allowable margin of error is also 5,700 years. In other words, this method doesn't work, at least not for dinosaurs for sure. It's exactly the same story with all the other isotopes of different chemical elements. No matter which element a geologist, paleontologist, or historian chooses, they will be measuring not the date of the organism's life, but the lifespan of the isotope that somehow ended up in the organism. The isotope itself is formed outside the organism and wanders in nature for an unknown amount of time. The very definition is based only on the assumption that the isotope enters the organism immediately after its formation and then never leaves. But is that really the case? So we discard the radiocarbon method. What other dating methods do we have? Uranium-Lead method. This method is similar to the previous one in its basic principle, meaning it determines the age by the rate of decay of a radioactive isotope, but it uses the decay of uranium-238 to lead. This method has an undeniable advantage in terms of dating time. The range of dates extends up to as much as 4.50 billion years, which, by the way, very suspiciously coincides with the estimated age of the Earth. However, this method also has its major drawbacks. First of all, the material being analyzed is usually not present in organisms, unless, of course, they eat zircon or granite for breakfast. That's why this method is used to date geological layers. And then when they find remains of living organisms in those layers, like someone's skeleton, they conclude that the skeleton is exactly as old as the rock in which it was found. And again, the logic is ironclad, not even allowing the thought that the uranium isotope could have formed almost together with the planet and to travel for billions of years from the surface deep into the planet and back, and only then settle in the desired layer. For example, during an eruption. It doesn't have to be lava. It could also be in the form of hot mud. Such mud volcanoes are common all over the planet. Yes, in the Caucasus, for example. And the sample being studied could have even formed in space and arrived here on some comet. So, again, it's not at all necessary that the rock sample being studied appeared at the same time as the animal buried in it. By the way, the uranium that scientists study was also formed in space. It's the heaviest metal that exists in nature. And according to the generally accepted view, it is formed as a result of a first-generation supernova explosion, meaning a star that existed even before our sun appeared. And this is the exact date that scientists get based on the uranium-lead method. And although recent studies suggest that the appearance of uranium could have been caused by another event, namely the merger of neutron stars, For the most part, it doesn't really matter to us. The main thing is that uranium does not form on Earth in any way. Not at all. It forms only in space and only as a result of catastrophic star explosions. Moreover, a significant portion of uranium-containing rocks is located in the Earth's crust close to the surface, in sedimentary rocks. This once again proves that its main origin on Earth is precisely related to the deposition of cosmic dust containing uranium. In other words, 1 or 2 billion years ago, somewhere far away or nearby, a supernova exploded, or 2 neutron stars merged, thus producing masses of heavy metals from iron to gold, mercury, and uranium. All these materials traveled through space for a long time, maybe 100 years or maybe 1 billion. Then they ended up on Earth, wandered for a long time as dust or settled in mountain layers, or maybe even fell to the ground as a muddy rain, covering tons of dinosaurs. Then all of this was compacted for some number of years, and only after that was the rock layer found and dated. But in this way, what you get is the birth date of the uranium element, not the layer containing the sought-after animal remains. However, this is the basis of the relative dating method, which assumes that the atoms and isotopes formed at the same time as the layer, and therefore, the fossils contained in this layer belong to that period. On this same basis, conclusions are also drawn about the biosphere that existed at that time. How speculative and shaky this concept is can be traced right now. For example, coelacanth fish of the order Coelacanthiforms. Those very ones, thanks to which the animal world supposedly came onto land hundreds of millions of years ago, and which were considered extinct, the very ones from which the first terrestrial vertebrates appeared. Well, they were suddenly found alive and perfectly intact in the Indian Ocean. And notably, in 550 million years, they haven't changed at all. Did evolution just stop or something? Why didn't these fish keep crawling out again and again in other eras? So, some of them crawled onto land, changed, and gave rise to amphibians, then dinosaurs. And us as well. And to the rest, he said, brothers, I took all the cash with me, don't change anymore. Or how does it work? 500 million years have passed, and then they made it onto land only once. They then considered the fate of their fellow creatures and decided, forget it, who needs land anyway? Here's another example. If a paleontologist of the future suddenly finds a fossilized part of the bottom layer of the Black Sea, they'll inevitably conclude that Earth's biosphere during that period was exclusively hydrogen sulfide-based. It was inhabited exclusively by single-celled bacteria. Well, maybe also tapeworms, invertebrates, and at most chordates. And then apparently some kind of cataclysm happened, as a result of which the bacteria converted all the hydrogen sulfide into oxygen, and modern life appeared on the planet. Funny. But that's exactly how scientists describe the Cambrian explosion, except instead of hydrogen sulfide, the Precambrian version features an atmosphere made up of a mixture of ammonia, other nitrogen compounds, and carbon monoxide. 2. And real scientists know how fragile and shaky their conclusions are, so their materials are full of words like apparently, maybe, most likely, and so on. And now, let's take a moment to step away from the well-known history and look at the history of paleontology itself. People have always found the remains of fossil animals. This was not some kind of exception. Mentions of them go back as far as centuries before Christ, and all the way up to the century when the search for fossilized remains became a science. However, even in 1709, they were simply considered a consequence of the biblical flood, or at the very least, the result of past global catastrophes. Yes, actually, that's still considered true even now, if you think about it. However, by the end of the 17th century, attempts were already being made to somehow classify everything in 1800. In 1815, after 8 years of military service in the Royal British Army, a certain Roderick Impey Murchison, at the age of 36, retired. He married the daughter of General Keegonin and spent a couple of years wandering around Europe, enjoying the company of his young wife. And so, after almost 3 years, in 1818, seeking a new way to apply his talents, he joined the London Geological Society, where he proved to be extremely active. Thus, a society of like-minded people was formed, among whom were also Adam Sedgwick, William Buckland, 2 more Williams, and Charles Lyell. After exploring the southern shores of England, he completed his very first scientific work in 1825, and 6 years later, he became the president of this very geological society. His research focused on the Paleozoic era, during which lobe-finned fish transitioned onto land, giving rise to the first amphibians. It was he, Murchison, who, based on his early works, gave the name to one of the Paleozoic periods, the Silurian. If the strange name confuses you, it simply refers to the name of a Celtic tribe that lived in that area. This happened in the year 1835. And 4 years later, he discovered the next period, the Devonian. Once again, he didn't look far for a name and named it after the county where he found the deposits of this period, Devonshire. Meanwhile, his colleague Adam Sedgwick was not sitting idle either, and he discovered the oldest period of the Paleozoic, the Cambrian. Guess where that name comes from? That's right, it's just the Latin name for another area in Britain where the discoveries were made. And apparently, to avoid drawing too much attention to Great Britain, they decided to name the next period the Carboniferous, or in translation, the coal-bearing period, which pretty much speaks for itself. This layer contains the maximum amount of coal, meaning the remains of plants, trees, and various insects. An interesting fact, Charles Darwin was a student of Sedgwick, and their friendship lasted throughout Sedgwick's life. However, Sedgwick, despite their friendship, fiercely rejected Darwin's idea of evolution. Interesting, isn't it? A zoologist who personally discovered one of the geological eras and who regularly worked with a team of pioneers, having seen all the fossil species with his own eyes, rejects evolution. But let's get back to Murchison. Murchison's conclusions were so popular that starting from 1831, he was constantly elected president, first of the London Geological Society twice. After the second time, he immediately moved from the position of president of the Geological Society to the chair of president of the Royal Geographical Society. Another curious fact, as you can see, all the geological periods discovered by this group were found exclusively in Britain without any radioisotope methods, apparently relying solely on logic and their own imagination. Although they also explored Europe, particularly France and the Alps, these expeditions were apparently only meant to confirm discoveries that had already been made. However, the Devonian strata in Britain were ambiguous. There was no clear geological separation, and this supposedly led to significant doubts about the very existence of the Devonian period. And so, in the winter of 1840, Murchison came to an unexpected decision. To confirm the hypotheses, he needed to go to Russia. Where else? Isn't that an obvious reason? I don't know, but to me it seems far-fetched and poorly put together. But judge for yourself, the year is 1840. Only 25 years ago, the Napoleonic Wars ended. And even about them, nothing much has been written yet. All the sources that tell us about them are dated exactly 1838 to 1840. Lev Tolstoy is still 12 years old, and he's running after the peasant girls. And history is only being written. All of history, most of the primary sources or records that we know of, were written around these years. There is still no exact data on the geological layers of Siberia either. Of course, geographical research had been conducted since the time of Peter, and even earlier, but there is no information about the geological layers. And if such data exists, they are not dated as Silurian, Carboniferous, or Devonian, simply because these concepts had just been invented. However, Murchison is convinced that going to Siberia, specifically the Urals, is essential. What is this manic attraction to Siberia among Europeans? Napoleon, Hitler, Murchison, Whitson, and a legion of others like them. So, Murchison enlisted the support of the Russian government, took the French paleontologist Vernel with him, and set off for St. Petersburg. The entire expedition was sponsored by the Russian Minister of Finance, Konkrim. At the beginning of June 1840, the expedition itself began. After inspecting the surroundings of St. Petersburg in just 5 days, the colleagues moved even further. They visited the banks of the Volkhov and Sias rivers, as well as Lake Onega. They headed toward the Petrozavodsk area in a light carriage, equipped with 5 or 6 horses, traveling at a speed of 30 to 40 kilometers per day. Without maps, relying only on the directions of local drivers and peasants, they spent the nights in the first huts they came across and at roadside inns. Murchison and his companions traveled from the coast of the White Sea along the banks of the Pinega, Vizigra, northern Dvina, Sukhona, Yug, and many other rivers and streams all the way to the Volga. Near Yaroslavl and Kostroma, where they met with Meindorf. From here, the travelers went to Moscow. Then they traveled to Nizhny Novgorod, Murom, Yalatma, Kasimov, Ryazan, explored the coal deposits of the Moscow region, and on the way to St. Petersburg, they studied the geological structure of the Valdai upland. It was truly a high-speed journey through terrain that is difficult to traverse even now. You can see what these places look like now on Katichansky's channel, who, by the way, is currently restoring an old merchant house in that area. What I mean is that even now, with an off-road vehicle, you would hardly be able to travel this route that quickly, especially considering that you don't have any maps and are traveling only by following the directions of the local residents, communicating through a government-provided interpreter. And at the same time, you absolutely have to examine the riverbanks and rock outcrops, which means going into unexplored places. Hearing this, it's easier to believe that the journey was made not on horseback, but in some kind of hot air balloon. Fortunately, they already existed at that time. And it's also easier to believe that this was a reconnaissance trip to specific locations with the goal of discovering something that could be seen right on the surface. And again, in my opinion, a balloon is much better suited for such purposes. Well, that's how it is. No matter how much we doubt the true intentions of the retired captain of the Royal Dragoons, he managed to dig up a couple of fossilized shells in the river sand. He declared it a discovery, leading to his immediate second appointment as president of the London Geological Society. If you think I'm somehow belittling his discovery, go to the banks of the rivers near Moscow, or even better, somewhere near Petrozavodsk, also to the riverbanks. And after the 5th or 6th scoop with a shovel, you will definitely find something, some kind of ammonite or belemnite. That is basically the same thing that Murchison found, but apparently inspired by government support and by the fact that Alexander II personally gave him his attention. Our Murchison. He decided to organize another expedition the following year. This time it lasted almost half a year, but the distance covered is impressive. In 5 months, the expedition traveled from the Baltics to St. Petersburg, then explored the Moscow region again, after which it headed to Vladimir, then through Nizhny Novgorod to Kazan and beyond. I couldn't find the expedition's exact route. However, it is mentioned that they visited both the Donetsk coal basin and the shores of the Sea of Azov. Then they headed to Yekaterinburg, crossed the Ural Mountains at least 8 times, reached Perm, and then returned to St. Petersburg. Even by the most modest estimates, that's almost 9,000 kilometers. Even considering that the expeditions sometimes split up to cover more ground, the speed is still fantastic. That means at least 50 kilometers a day for 5 months through rough terrain, rivers, and mountain passes. Every single day. Even now, such a route would take at least 7 days by car. When they actually found time to study anything remains an open question. The only thing you can really do at such a pace, in my opinion, is to look at the surroundings from a carriage window, from a boat, or, as an option, from a hot air balloon. Nevertheless, along the way, Murchison discovered a new prehistoric era, which he named, following his old habit, after the place where the discovery was made. That's how the Permian geological period appeared. So what did our geologist actually see practically on the run? I doubt he had any opportunity to conduct any meaningful excavation, yet he saw a huge number of remains of prehistoric animals. So huge, in fact, that to this day, the end of the Permian period is considered the Permian Extinction, the largest in the entire history of the Earth. Now let's take a look at all the events again, but briefly, without any speculation, just the facts. From 1799 to 1812, the Napoleonic Wars were raging in Europe, ending, well, with the fire in Moscow. In the previous episode, we found out that at that very moment, a foreign object appeared in Earth's orbit, and not just one. A retrospective analysis of the orbits of nearby comets using a National Aeronautics and Space Administration tool showed us this. About 20 years later, world history begins to be written. Yes, almost all sources, even about the war with Napoleon, were published after 1825, even if they are officially dated earlier. The peak of discoveries begins precisely in those same 1830s and 1840s in 1825. Teams for studying the Earth are being formed in Britain. In particular, our team consisted of former military captain Dragoon Murchison, a former pastor Adam Sedgwick, another theologian William Buckland, and military treasurer Charles Lyell, who suddenly became geologists and zoologists. This team quickly finds the remains of prehistoric layers and animals, classifies them, and creates the first stratigraphic tables. There was no radioisotope method at all at that time. However, since then, no significant changes have been made to their conclusions. After that, the team sets its sights on Russia and is eager to explore its north and south, from Arkhangelsk to Azov, from Astrakhan to Perm, and everywhere they find traces of extinction, which they called the Great Permian Extinction. But what if it didn't happen 250 million years ago, but much more recently? What if the expeditions rushed to see what was left at the site of some great power and saw only a land that had died out? The speed at which they traveled didn't allow them to conduct any deep research or excavations. However, it was repeatedly reported that the expedition split into several groups multiple times and then reunited after thousands of kilometers, relying only on the directions of the local inhabitants. Yes, try now to go with your friends by car for just 200 or 300 kilometers to an unfamiliar place, and agree to meet at a set time in a place you've never been before, without using phones or navigation devices, only stopping and asking the locals for directions. I bet that if you even manage to meet at all, you'll spend much more time looking for each other than on the actual trip. But our travelers went by wagons, boats, on foot, and on horseback, through rough terrain and forests, across rivers and mountains, and still managed to meet successfully after thousands of kilometers. This shows that Murchison's expedition had extremely accurate maps. They knew exactly where to go, which roads to take, and which direction to look. Thus, this looks more like reconnaissance on a battlefield than a geological expedition. But what about the stratigraphic tables that show different types of creatures depending on the depth and the layer they are found in? They don't matter. If you take a cross-section of the Earth's biosphere right now, it will look almost the same. In the Earth, there will be bacteria. If it's a swamp or the seafloor, then fish, shells, trilobites. A bit higher up, there will be lower vertebrates and amphibians. Higher up is the soil, on which, of course, there is a forest. By the way, if it gets knocked down, for example, by a shock wave, it will fall flat, mostly bearing the insects that live right there, among the trees and inside them. And even higher up will be the large animals that manage to survive in the fallen forest and make their way to the surface. And cover all of this with a thick layer of clay, sand, and ash. There you have your stratigraphic table. Remember, at the beginning of the video about the biosphere of the Black Sea, and once again, remember one of the researchers, Adam Sedgwick, Darwin's teacher. He never supported the theory of evolution, not even for a second, despite seeing the fossil remains with his own eyes. And radioisotope methods appeared much later and have been used ever since, mainly to prove the correctness of those first 4 people, 2 pastors and 2 military men. To be continued. Subtitles created by